morning, welcome to our next lecture on computational heat and fluid flow. We have been discussing higher order finite volume methods. Actually, we started just on that last time. So that is then chapter 6. Higher order finite volume methods. There is also the term high resolution methods that I just mentioned. High resolution methods. That term is, for example, used by Randy Levesque in his book on finite volume methods. That means that we have at least second order in the smooth part of the flow, and at discontinuities that we do not have oscillations. And that is then the topic of our first chapter here, our first section in this chapter 6, that is higher order. If you look at TVD, total variation diminishing methods. So those are the methods that avoid that we get the Gibbs phenomenon, that is oscillations, because with oscillations the total variation would increase, but we do not allow for that. So then the idea was to replace what we have been doing so far. We have a cell. In our case, we focus on the cell with the cell J with the midpoint xj and the left boundary xj minus 1/2 and the right boundary xj plus 1/2. And if we have here the u, then what we compute, that is actually in finite volume method, it's a cell average. It's a mean value. And we argued that for the exact solution, we can place that at some point, and the point where we place it best is the midpoint, because then the average of the exact solution and the point value at the midpoint differ only by delta x squared. So what we want to do now is to replace the reconstruction that was used by Godunov in his method, where he assumed that we have a constant distribution, by some linear distribution. So that was what we ended up last time. So that will only give us first order methods, but when we manage to get a linear distribution, for example, we can represent then linear functions in a better way, and we get then more accurate solutions. And so in that case, we call this reconstruction. So from the mean value, and actually you'll see from the mean values, we need more than just the one. We get how the function looks like in the cell. So from the cell average, we get how the function looks like. And then our goal is to have a linear distribution. So if we look for the cell J, then we want to have something like that we introduce the slope uj prime. So if we have the uj prime, the slope, we multiply by the distance, then we get the value of this red curve, of this line. So the question is how to determine this slope. So that is now the question, and there we can do it in the following way. We do it, remember what we are going to do is, we're going to use this for the Riemann problem, to get proper left and proper right states. So we do then first for the left state, and there we do, we call that the left reconstruction. So for left reconstruction, that is when this is the cell, and we are focusing on this cell face, then we want to know what is the value there on the left side. We'll have also something on the right, and from that we do a right reconstruction. But first we use left reconstruction. And that is then, and we do that in the cell J, that one that we are focusing on. And there it is common to use in this equation 1 the following, that is then 2 A, that we say we approximate the derivative, the slope, in the cell J by the left neighbor. So we take the left neighbor into account, uj minus uj minus 1, and divide by the distance. So then we have a valid approximation of the slope. And you see it here in the, yes, we have it here. But here I did not use the left slope, I did use something else. We will come to that. Anyway, so that is a way how we can do that. And we shall denote this, I define this, I denote this this way by these 2 points, by delta x uj plus 1/2. So that is the definition, so to speak, of sorry, this is not wrong, it's wrong, it is minus. So we take the value from the left. So then, and then from that we get then the left reconstruction at the face that we are interested in. So imagine what we are doing here. We are taking into account a neighbor. So we have here a neighbor xj minus 1. If we are using this slope, then we must be here, so that this slope then is given by this, the slope from uj to uj minus 1. So that is this value. So that is what we are doing here. So we take this slope defined by then this slope that we have here inside the cell J. And that will give us then the left reconstruction at the face xj plus 1/2. So that gives us then the left reconstruction at the face xj plus 1/2. And that is what we get. You see, we take the 2b later. So we first take the left side. How does that work? Well, we have it here. We have here the uj, and we have then here this approximation. And now we go here to xj plus delta x/2, right? Because this length is delta x, and this distance is delta x/2. So x minus xj, if we are at this point here, then this distance is delta x/2. And we have here delta x. So in the end, we can write it in the following way, and I write it in a general way first. Later on, we get it to this simple form that I just mentioned. So we get the uj, and now we take the delta xj. So we take now into account that we might have different length of the different cells. So that is the length then of delta xj. This is this length between the right and the left faces. And we multiply by our slope. That is what we called here the delta x of uj minus 1/2. So then we have found the value here. So that is the result of this procedure is that we have the value here. So that is the value. This value here will then be our u left j plus 1/2. So u left j plus 1/2. So and in the same way we do it on the right side. On the right side we then take into account a neighbor that we have here, and then do that in a similar way. And actually we need two neighbors, because we need to do the reconstruction in the cell j plus 1. So we need to go to the cell j plus 1 and do it similarly. So that gives us then the following. Maybe we can write the figure now to complete this. So we now extend the figure now to also include the cells j plus 1 and even j plus 2. So we have x here. Let's see, we need 4 at least. 1, 2, 3. Like that. Yes. And we are focusing on the face. So we have here the u. And here we are at the face xj plus 1/2 that we are focusing on. And now we are repeating what we had already seen there. We have the xj and the xj minus 1, but now we add also the cells, and here I write the midpoints, xj plus 1 and xj plus 2. And what we assume to know is just the cell averages. In our example, we had here the value, that is the uj minus 1, uj minus 1, and then we had here the value uj, and that was then, this slope was then used to get the reconstruction inside the cell j. So we used then this slope here to get then the value uj is 1/2 L. So that was the value. Let us again indicate this. So that is then uj plus 1/2 left. It's a left reconstruction. And there we need then the reconstruction in the cell j. Now we do the reconstruction in the cell j plus 1. Now we assume the following. We assume that we have a cell average here, which is the uj plus 1, and we assume, let's say that we have here the uj plus 2. Then we do it in a similar way, but now we take the slope between uj plus 2 and uj plus 1. So we have then this slope here. So that is now our slope. And we use that to get the reconstruction in the cell j plus 1. So in this cell here, that means we then use, we are here, we use this slope to get the value here. And the value here then, that is then the value from the right reconstruction. We are again at the face, but we have reconstructed from the right. So we have two values, on the left and on the right. And that is different from Godunov. Godunov would have taken here the constant value, uj, he would have taken here the constant uj plus 1. But we do a linear reconstruction to get higher accuracy. So now we have just to formulate in a similar way as we did it for the left reconstruction, what we have seen here already illustrated, just to formulate that in the mathematical way. So then we do the right reconstruction. So for right reconstruction, and that we do in cell j plus 1. So there it is common to use the following approximation for the slope in our equation 1. This is 2b. And then we do the slope in the cell j plus 1. And then we do what we have already seen here. We take the slope in this way here. So this is xj plus 2 minus xj plus 1. And this is uj plus 2 minus uj plus 1. In that case, it's negative. So then we write that. It's uj plus 2 minus uj plus 1 divided by xj plus 2 minus xj plus 1. And we can give that also a name. That's the definition. then, and that will be then the slope across the face j plus 3 half. You think of it here. So what we do here, this is the face j plus 3 half. And we take the slope across that face. So, and from that, we get then the right reconstruction at the face xj plus 1 half. So that is the right reconstruction at the face xj plus 1 half. And that is then the following. We simply insert then this approximation in our equation 1. And then we are interested in uj plus 1 half again, and that is then the right one. That is then, we start then from the midpoint of that cell j plus 1. Now we have xj plus 1 minus xj plus 1 half. So that will give us then minus delta x j plus 1 half. Because we are starting here, and then this distance here is delta xj plus 1 half, negative, times the slope, and the slope is the one that we just denoted by delta x uj plus 3 half. So then we have the right reconstruction at the face xj plus 1 half. And that is what we indicated here. So this value here is then the right reconstruction. So there are other possibilities that you could use. You could even use quadratic reconstruction. But in any case, what we get in the end are two more appropriate approximations of the function at the face. And these are then used to solve the Riemann problem for our case. Let's see. So the goal is to use in the Riemann problem the following. That is the Riemann problem. That is, in our case, we have a scalar one-dimensional conservation law. And then we have flux function, for example, u squared half for the Burgers equation. The x derivative of that is equal to 0. So we are using again the mathematical notation where the indices define derivatives with respect to time and space. And we have a discontinuous initial condition, piecewise constant, and that is a constant u left on the left of the face. We are considering the face j plus 1 half. And we have a condition right for x larger than xj plus 1 half. So in this Riemann problem, we use now this extrapolated u left instead of the uj. So we use then here the ul is then equal to the left reconstruction uj plus 1 half l instead of what Goodenough did, instead of uj. And similarly on the right, we use u right equal to the right reconstruction j plus 1 half. And that we use instead of Goodenough's uj plus 1. Goodenough would have used this here, but we use more accurate one. So that is our goal. That's what we want to use, because then we get inside the cells higher accuracy, and by that we get higher accuracy of the values at the faces. But there is a problem. If we do this, we get oscillations. So the problem with that is we get oscillations, so we have to modify this approach. You can see almost in this example what might be the problem. When we have this here, we might get here a value that gets simply too large. So we might get some overshoot, and in fact we get oscillations for this. So this doesn't work. So we note that we get, in this case we get oscillations. So problem with this approach that we just characterized are oscillations. And they occur actually at extrema. And I have of course chosen an example for that. There we have a maximum in our example. However, there is a nice solution to that. The solution is the use of what is called slope limiter. So that is, as the name says, to reduce the slopes. To reduce the slopes, and in particularly at extrema. In our case, the slopes that are involved are at the face j minus 1/2 and at the face j plus 3/2. So they are reduced at extrema. So how do we do that? Well, if we start with the extrema, then we have here the example. Here, for the right reconstruction, we use the slope from uj plus 2 to uj plus 1. And we get this slope here, which is negative. But we could also have used, it would also have been an option, to use the slope between uj plus 1 and uj across the face. We could have done that, but if we had done that, we had seen that that slope is positive. So here we have a positive slope, here we have negative slope. And if we have this situation, we have an indication of an extremum. And in that case, the rule is don't do anything, just do it as good enough, take the constant. So in that case, the solution is that we take the slope equal to 0, and we get then here the slope limited value that we also would get from good enough. So that is the idea here. So that is then with the slope limiter. So that is then the value that we get here then. Let's see, out of space here. So this value here would be then the uj plus 1/2 right, and we do not take this one here. So that would be the one with the slope limiter. On the left, we have a different situation. We use the slope from uj to uj minus 2. But we could also use the uj plus 1 to uj. And in that case, we say we take the slope that is smallest in absolute value. In this case, it happens to be this slope here. So in this case, we get the same one with the reconstruction. We take this slope, because that slope is smaller than the slope between uj plus 1 and uj. So in that case, we have then the slope limited one, the uj plus 1/2 left, is then equal to the one that we had from in the first place. So, but that was just a coincidence. So now we want to formulate that in mathematical terms, and we might say what we have done now. That is cell J, what we just discussed, that was the last thing we discussed. We had both slopes. That is the delta x that we originally used, J minus 1/2, and the slope that we now also consider, that is the slope across the face, J plus 1/2. They both are in that case positive in our example. Then the limiter that we will choose is called Minmod limiter. You will get the definition in a minute. So that limiter, Minmod limiter, then chooses the smaller one. The smaller one, we should add in absolute value. In absolute value. So we'll see that shortly. So there, the magnitude of the slopes are compared, and the one that has the smallest magnitude that is chosen. In the cell J plus 1, the situation was different. In that one slope, that was the slope delta x uj plus 1/2 is positive, and one slope, that was the one that we used for the right reconstruction in the beginning, j plus 3/2, is negative. And in this situation, the Minmod limiter chooses the slope 0. So Minmod limiter chooses slope 0. So that is what it is acting, and that is the latter one with the getting back to the constant reconstruction by Goodenough, that is essential at extrema. So then we can also give that then formula. And let's see. A little bit further here. So that is the illustration of what we have discussed. So now we finally arrive at the slope limited MUSCL approach that was developed by Brown van Leer. It was actually in the 70s that we already did that. 70s or 80s. And the following, we get the value on the left of the face by taking the value in the cell J and adding delta xj½ times the slope delta x uj. And that is then defined by comparing the two slopes. That is defined in a minute. And the value, that is the left reconstruction. And the right reconstruction that is uj plus 1/2 right, that is then obtained by the value in the cell uj plus 1 minus the length of that cell uj plus 1/2, and here we look then at the slope that is related to the cell uj plus 1, that is also defined shortly. And where the limited slopes, that is the delta x, the delta x uj, and we shall not focus on that, but once we know that, we also know the other one. They can be defined by different limiters. In the lecture notes and also in the textbook, you'll find other limiters than the Minmod limiter. But the most common is the one that we already started to discuss, the Minmod limiter. So most common choice is the Minmod limiter. And that is then defined in the following way. We do it for the cell J. Then we take the Minmod, that is a function, and we compare then two slopes. The one is to the left, that is uj minus 1/2, and the other is to the right, u delta x uj plus 1/2. So you see it in this example. Let's see. So we have the slope delta x uj minus 1, that is between uj and uj minus 1, this slope, and uj plus 1 and uj, that is the slope that is related to this face. So these slopes are then compared, and if you want to know the uj plus 1, you just shift the index. So we can write that. You replace the j by the j plus 1 to get then the slope that we use here, the uj plus 1. So that is then the Minmod of delta x. So this is just, this becomes j plus 1, so this becomes then uj plus 1/2. And this becomes j plus 1, so we get uj plus 3/2. Delta x uj plus 3/2. So then we know that. And now the definition of the Minmod. Let's see. So the Minmod is defined as follows. That is 6. And the Minmod is a function of two arguments. In our case, two slopes. We call them A and B here in definition. And then we have three cases. We get A if the modulus of A is smaller or equal than the modulus of B. And it is important if they have the same sign. So in our case, on the left, both slopes were positive. So then this product was positive. So, and then we take the one that has the smallest magnitude. In that case, it was the slope to the left. If that is not like that, but we have still the same slope, imagine that the uj plus 1 would have been say, equal to uj, for example, then we would have taken the slope on that in that direction. It would be b if the absolute value of b is smaller than the absolute value of a, and the product is positive. And if the slopes would both be negative, then the one would be chosen that has the smallest absolute value. And we get 0, that was the case for the right reconstruction, if the slopes vary in sign, or if one slope is 0. So that is the definition. However, when you do the programming, it makes sense to use a more suitable form for that avoids these if statements. They usually slow down the computation. And the way you can do it is in the following way. The sine is also a MATLAB function. You take the sine of A and multiply by the maximum of 0, the minimum of the following absolute value of A and the sine of A times B. So of these two, you take the minimum, and then let's see, the maximum is then, we do it like that. Okay, so that would be then the Minmod limiter, definition of the Minmod limiter. You can do that also for vectors. So when A and B are vectors, then you have just to remember that you have to put a pointwise multiplication here, and you have to put a pointwise multiplication here. So then you can use it for, in MATLAB, you can use the colon notation, get computational efficiency by that. So now we can further simplify things when we have equidistant grid. So what I explained to you here, that is general. You can use any general grid. Yes?
Could you explain the last line again, please?
The last one?
Yeah.
Well, it's just what is above. So you can take the sign A is positive, then this here gives just a plus sign. If the sign A is positive, this is the absolute value of A, and this is then just a plus. So then this is the minimum of A and B.
Okay.
And then you look then for the maximum. Imagine the B would be negative, for example. Then you would get a B on this side, but here you take the maximum, you get a 0. So it does exactly the thing. So let us then specialize for an equidistant grid. In an equidistant grid, we assume that the grid spacings in each cell are equal. And then we use that in 4. And then that was 4, let's see. That was, I think, that was the original MUSCL approach, where we started off with. So that was the slope-limited MUSCL approach. Here we have it. So then we don't need to distinguish here between delta xj and delta xj plus 1. It's just delta x. And these delta x, these slopes, contain also a delta xj or delta xj plus 1 in the denominator. So they will cancel. And then we get a much simpler form. So then we can write this then in the following form. So we get then, let's we get the following. That would then be 7a. That we have then the uj plus 1/2, that is the left reconstruction, is equal to the value that we have from the beginning, plus, and now we directly introduce the Minmod. And then the Minmod is then acting on the differences, because the delta x in the denominator on this one, and also here they will cancel. And then we just get the Minmod, and that is then having the arguments uj minus 1, and it has the argument uj plus 1 minus uj. So that's all. And similarly, for the right reconstruction, the uj plus 1/2 right is then taking the uj plus 1, and now we take minus 1/2, and then we have the Minmod, and the arguments here are then the same as this one, uj plus 1 minus uj, and the other argument is uj plus 2 minus uj plus 1. So that is all. So when you want to do that, and you have equidistant grid, you just need the Minmod function and to compute that. Yes?
So beyond delta x?
No, you don't need to do that, because the delta x here contains, for example, the uj plus 1 minus uj divided by xj plus 1 minus xj, which is delta x. That goes away with that. So therefore, delta x disappears. Everywhere it disappears. So therefore, there is no delta x. It is just the value in the cells and then plus or minus some difference. Okay, so you see, regarding programming, all you need to do is to have a MATLAB or just an autonomous function in MATLAB. You can do that in the function that you have. You can define that. Then you have the Minmod as a function of 2 arguments. And then you just do this. And then you feed your Riemann solver, not with uj, but with this, the extrapolated from the left, and not with uj plus 1 from the right, but with the extrapolated one. That's all. The Riemann solver that you use, upwind method or Lax-Friedrichs, local Lax-Friedrichs, Godunov, whatever you like, they can be the same as you used for the first order problem. And by that you insert just more accurate arguments in the Riemann solver. That's all. So that makes this approach so nice. So once you have a solution for the first order problem, you can very quickly get it to higher order by this approach. We have, of course, a little catch at the boundaries, because the Godunov method only needs here the neighbors on the face, the left neighbor and the right neighbor. But you need more. You also need the uj minus 1, and you need here the uj plus 2. So you need 2 cells more. So at the boundaries, that has to be taken into account. And that limits also its application at the boundaries. If you have just directly boundary conditions, then you can only go, you cannot do it directly in the first cell. But for our problem that we are doing in exercise 4, we can do it because we have periodic boundary conditions, and then the boundaries are essentially no problem. Because we know we have the data from the periodicity condition. So when we have done this MUSCL approach and we have found the extrapolated values, then the Riemann problem that is the following. 8, where we have the, well, it is always the same. We have the initial condition, we have our conservation law, ut plus f of u f of ux f of ux is equal to 0 with this initial condition u of x0 is equal to the ul is now the left extrapolated at the phase j plus 1/2 for x smaller than xj plus 1/2, and the u right is the right reconstruction with the slope limited MUSCL approach. And that is for x greater than xj plus 1/2. So that Riemann problem, that is essentially, that is the Riemann problem here, is solved by a suitable, we call that the Riemann solver. And which is TBD for the constant reconstruction. So the Riemann solver we can express as 9, that we have a flux function that we get, which is a function of just the states on the left and the right of the Riemann problem, that is of UL and UR. In the one that we have been discussing for Godunov method, then the UL was the UJ, and the U right was the UJ plus 1. But here we have then better values. So they are then used instead of what I just said. They are used, that means it est instead of uj and uj plus 1 for first order TBD schemes. Okay, so instead of these, the extrapolated values variables that are then the uj plus 1/2 left and uj plus 1/2 right are used. So that is the only difference. And the nice thing is that with this approach we get higher order away from extrema. Near extrema we fall back to the first order method. So the resulting we could say that is a higher order scheme, that is a high order scheme, that is an example of a high resolution scheme, is in the first place, that is a good thing, it's TBD, but it is only first order at extrema, but otherwise second order. So that is the big advantage. Okay, so then you have seen this example, and you've seen the principle. After the break, I'll give you the example that you need for exercise 4. It's just an application of what we discussed. Okay.